Okay, in our last video, we worked with KSP and solubility. In this video, we're doing the same thing, but one difference is we're going to take a look at how KSP works and solubility works when there is a common ion. So in the previous video, we had in our ice table, we had some compound like I don't know, whatever, something that doesn't dissolve well. Okay, and we had the two ions, and we had these were both zeros when we did that problem, and then we just did the problem like that. Okay, so what if these are not zeros? What's the effect? What's going to happen? So we'll see it by the end. We're going to be tying this in with Le Chatelier's principle, and it's also kind of like a buffer concept as well. When you'll see that when there is something there, and I'll try to repeat this a couple times throughout the video, when there's something there, it blocks. You could kind of think of it as like blocking how much is going to go over to the right. Okay, so keep that in mind when we do this, when we work through these problems, is that concept's a very recurring theme in AP chemistry. So it happens with buffers, so acids and bases. It happens with solubility. Well, basically it happens with all the different Ks you can have. So it happens with all the different equilibriums. If there's something there, it won't go there as much. It's Le Chatelier's principle. So this first problem says, what's the solubility of calcium carbonate in a 0.3 molar sodium carbonate solution? So we'll set up our ice table as normal, and we're going to write calcium and carbonate ions over here. Okay, and we'll dash out our solids as normal. And this is going to be, instead of a 0, so the calcium will be 0 at the beginning, but here we have, this is going to dissociate in water is fully soluble, so you'll get this and this. You get 2 sodiums and 1 carbonate ion. So our carbonate ion is going to be 0.30 molar at the beginning, so it won't be 0. So this will go up by x. This goes up. Remember to bring down the coefficients into the change line. So this will go up by x. So this is x, and this will be 0.30 plus x. You'll see that the nice thing about these KSP values is they're ridiculously small. So the assumption rule is almost always going to work. There are some times where it won't work. We're actually going to encounter one of those times in this video. So this we're going to assume is very small. And of course, you could easily check that at the end. Is very small relative to the 0.30. So we're going to assume that that's 0. And it makes this much, much easier. So we'll solve for x. So our KSP is 8.7 times 10 to the negative 9th equals x times 0.30. Okay, so x in this case will be 2.9 times 10 to the negative 8th moles per liter. Okay, now it says, what's the solubility if it's 0.80? So we more than double the amount of CO23, or carbonate ions, CO32 minus. So calcium carbonate dissolves by this equation again. Dash this out, 0, and this time it's 0.80. So this will go up by x. This goes up by x. We know that it has to go to the right still because there is nothing there. So that needs to have some number there. So we know for sure it needs to go to the right. Because right now, if we calculated it, q would be 0. So there's got to be something that goes over there. So this would be 0.80 plus x, assume. So now we have 8.7 times 10 to the negative 9th equals x times 0.80. So now if we punch this into our calculator, I get 1.1 times 10 to the negative 8th molar. So a conclusion that we can make is They seem to prefer writing it moles per liter. So our conclusion that we can make is, notice that when this increased, okay, our solubility went down, which makes sense with Le Chatelier's principle. When that number goes up, it's not gonna go over to the right as much as it did here. So here it went more than twice of what it is here, the solubility. So because we more than doubled our amount of calcium carbonate, so we can make a conclusion here, and this is a real general conclusion that works with all of these. So if there's a common ion, or you increase the concentration of that common ion, as we did here, it makes the solid less soluble. And it's because Q, it's because your product side doesn't have to increase as much. It doesn't have to increase as much for the equilibrium process to reach the KSP value, the KSP constant, because there's something there. Okay, so if they were both zeros, it needs to increase more to reach KSP, in other words. Okay, so we're going to cover a special instance where the common ion effect and solubility and pH. So in this specific instance says, watch out for solids that make OH minus. The common ion effect will occur. So remember water. So when you look at your K, we know that hydroxide's insoluble, okay, except for group 1 and below magnesium in group 2. So these are typically insoluble, except group 1A and group 2A below Mg. So calcium hydroxide, strontium, and barium hydroxide, we know those are strong bases, so those are going to be fully soluble. So what does this have? What role does this play? So we're going to use this as an example, tin hydroxide, in the following calculations. So we're going to do it in pure water. We'll do it in a solution buffered at pH of 2 and a solution buffered at a pH of 12. So first we're going to do this problem. We're going to see what the solubility is like in neutral water. Okay, so our OH concentration is going to be different in all of these. So OH, so keep that in mind, is different in all three of these. Okay, and we're going to reflect that in our ice tables when we do these problems. So if you have tin hydroxide, it's going to make a tin ion and 2 hydroxides. Okay, so this is going to be 0, but I'm solving problem A, by the way. But this number right here is 1 times 10 to the negative 7th because it's neutral water. And so the solubility, these numbers are so small that these numbers, they don't have to be very big. They could be really, really small. And as we see, this is small, but these are so small that nothing hardly goes over here. So it's actually going to play a role in the solubility, is the autoionization of water. So this is 1 times 10 to the negative 7th. So it's not 0 here. Not 0. Okay, this number goes up by 2x. This goes up by x. So this will be x. This will be 2x plus 1 times 10 to the negative 7th. And we're going to use the assumption rule here. You'll see that on this one, the assumption rule won't actually work because it's going to be the amount of OH will actually is so small actually affects our calculation. So okay, so where am I at here? Okay, so 3. Okay, so I get 3 times 10 to the negative 27th equals x, or actually, let me write this out. Okay, and this is going to be squared. So I get 3 times 10 to the negative 27th equals x, and I'm going to use the assumption rule, so 1 times 10 to the negative 7th squared. So x equals over 1 times 10 to the negative 7th squared. Okay, and then x would be 3 times 10 to the negative 13th moles per liter. Okay, and you could verify the assumption rule works. It should work. So 2 times this number is not going to add anything to this number. This number is still too small. Okay, so that's the solubility in neutral water. Okay, next we're going to do B, where pH equals 2.0. So here's our ice table on that. Okay, so get rid of the solid. This will be 0. This will be x. So here, our pH is 2.0, so we need to find the OH concentration. So the OH concentration, POH would be 12. So OH would be 10, 1 times 10 to the negative 12. That's what goes here, 1 times 10 to the negative 12. Okay, you'll see that this is actually so small that it will actually play a role. We won't be able to use the assumption rule, I don't believe. So this will go up by 2x. This goes up by x. So this will be 2x plus 1 times 10 to the negative 12. Okay, now this number is so small that x can have an impact. I can tell just because it's so small. So our KSP is not small enough. It's actually big enough to affect this number here. So let me reduce this problem to this. I end up getting this 3 times 10 to the negative 27th equals x times 2x plus 1 times 10 to the negative 12th squared. Okay, now if I combine all my like terms and I distribute and I factor this out, then I end up getting this. I get 4x cubed plus 4 times 10 to the negative 12th x squared plus 1 times 10 to the negative 24th x minus 3. I did this beforehand because I knew this was going to happen. So let me show you on your calculator how to do this. So I'm going to turn this on. And I go into apps, and I want this polynomial solver. Okay, and I'm going to go polynomial root solver. And here I'm going to select the 3 right here. Okay, and then I'm going to, I want the decimal, so now I go next. And now I enter my numbers, so I go 4 here. I go 4 times 10 to the negative 12th. And then 1 times 10 to the negative 24th. And then a negative 3 times 10 to the negative 27th. Okay, and then I hit solve. Okay, and then there's my answers. So I get 9.1, or actually it's 9 because this number only has one sig fig, times 10 to the negative 10th. So my solubility is 9 times 10 to the negative 10th moles per liter. Okay, so for part C, I have pH of 12.0. Okay, my ice table is going to be the same, so I'm going to come up with this. I'm going to skip my ice table on this. Now on this one, your OH is going to be 10 to the negative second. So your assumption rule should totally work because this number is too big for that KSP value to have an impact. So this is going to be x, 2x. We're going to assume that, so on this one, it's safe to assume that the 2x is fine. Okay, so this is going to be 1 times 10 to the negative second here, and then squared. So x on this problem is going to be 3 times 10 to the negative 23rd moles per liter. Okay, so what does all this mean? I'm going to summarize this in the following table. So when the pH was 12, don't go to that yet. So when the pH was 12, my hydroxide concentration was 1 times 10 to the negative second. Okay, and then my solubility of tin hydroxide was this. When it was neutral water, the pH was 7. This was 1 times 10 to the negative 7th. And this was 3 times 10 to the negative 13th. Oh, sorry, this was 3 to the negative 23rd. Right here was the pH. When the pH was 2, this was 1 times 10 to the negative 12th. And our solubility was 9 times 10 to the negative 10th. Okay. If we apply Le Chatelier's principle here, okay, when this number was increasing, okay, so we see the effect on the solubility. When this number goes up, this doesn't go over here as much. Okay, it kind of gets blocked when this number is so high on our ice table, so on the I line. Okay, and over here we see that when the number goes down, okay, over here we see when this number is lower, then more of this needs to go over. Okay, so when I cross this out, I don't mean it doesn't go over there. It still goes over there, but as we see it, than it was here, okay, on this one. Okay, so here's the your turn. It seems like my slide keeps wanting to go here anyway. So here's the your turn. Okay, so it says calculate the solubility, kind of like what I just did. And this one I chose one where the KSP should be small enough to where you could use the assumption rule on all 3 steps, okay, or on all 3 problems. So it says do it in neutral water, pH 4, and pH 10. Explain the outcome kind of like what we just did. Okay, and then here's this question. This is question number 2. Should be a 2 here. Would calcium carbonate be more soluble in a solution buffered at 2.0 or a solution buffered at 12.0? Explain your answer. It says use 2 different equilibrium reactions in Le Chatelier's principle. All right, so that's the end of our video.